Okay, this video is on recursive sequences. So what is a recursive sequence? Well, what we've learned about already are sequences that are recursive, but we don't give a recursive definition for. In order to give a recursive definition, we have to be given at least one term, or the first term of the sequence. Maybe the first two, maybe the first three. And the formula depends on knowing the previous term or the previous two terms. So it's not convenient because if you want to calculate the 100th term, then you have to know the 99th term or the 98th term as well as the 99th term or a few before. Okay, so here's an example of a recursive formula for a sequence. So in this one, you're given the first term, t1 is 7. The second term, t2 is 13. And then here is the formula for it. Okay, so the whole definition for the recursive sequence has to have at least the number of terms that are in the formula. Now this formula has that term number n, so if you want to calculate term number n, say term 10 or something, then that is going to be term 2 times term 10 minus 1. 10 minus 1 is 9, plus term 10 minus 2. Well, 10 minus 2 is 8. So term 10 would be 2 times term 9 plus term 8. So in order to figure out term 10, you'd need to know term 9 and term 8. So this n minus 1 means the term just before the one you're trying to figure out, and n minus 2 means 2 terms before the one that you're trying to figure out. Okay, so here's how you might calculate term 3. So term 3 on this is going to be 2 times tn minus 1, so n is 3, so term 3 minus 1, plus term 3 minus 2. Okay, 3 minus 1 is 2, 3 minus 2 is 1, so term 3 is going to be 2 times term 2 plus term 1. Now we know term 2 and term 1 from here, so we can calculate term 3. And we just plug those in. Okay, so term 2 is 13, term 1 is 7, so 2 times 13, 26, plus 7 gives us 33. So now we know that term 3 is 33. And how would you calculate term 4? Well, term 4 will be 2 times the term before it, which is term 3, plus 2 terms before it, which is term 2. So term 4 would equal 2 times term 3 plus term 2. And if you did that, well, 2 times term 3, so 2 times 33, 66, plus term 2 be 79. And that's what you get. Okay, so if you needed to, this is where it's inconvenient. If you wanted to find term 100, well, that's not very convenient because you need to know term 99 and term 98. And in order to do that, you have to calculate them all the way up. So you can't skip any until you get 99 and 98, and then you can calculate term 100. Whereas before, without the recursive definition, you could just have a formula, sub in 100, and you could calculate the term. Now, the two sequences that we've looked at so far, arithmetic and geometric, they also have a recursive definition for them. And it's fairly simple, so let's take a look at the arithmetic one. Okay, so arithmetic as a recursive, well, let's take a look at the formula. So this is the non-recursive formula. Tn equals the common difference times n minus 1 plus a. All right, so every time, so you start with the value a, and each time you add d to it. Okay, so for example, t1 equals a, t2 equals a plus d, t3 equals a plus d plus d. Okay, so the term 3 equals term 2 plus d. term 2 equals a plus d, which is t1 plus d. So in order to figure out tn, you're taking the previous term and adding d. So this is the recursive definition for arithmetic sequences. So you have to give the first term, t1 is a, and then tn is the previous term plus d. Okay, you have a similar process for geometric as a recursive. So as a non-recursive, this was our formula. First term times the common ratio to n minus 1. Okay, and the first term is a, the second term is ar, third term is arr. If you look at that, well, the second term is the first term times r. The third term is the second term times r. You keep multiplying by r to get the next term. So then the recursive definition is fairly obvious from there. t1 equals a, and tn equals tn minus 1, so the previous term, times r. So these recursive definitions for these sequences are unnecessary. You don't have to have a recursive definition for arithmetic or geometric. But there are some sequences that you need a recursive definition for. And there's one that is important, comes up again and again in all sorts of sciences, and it's called the Fibonacci sequence. So this is another example of a sequence. This one needs a recursive definition. So the sequence itself are these numbers: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Now the mathematical pattern for this is take these two, add them, and you get the third term. Then take the second and third term, add them, you get the fourth term. Then take the third and fourth term, add it, and you get the fifth term. So the definition for this sequence is take the two previous terms, add them together to get the next one. And so we only have a recursive definition for that sequence, which is this one here. Okay, so t1 equals 1, t2 equals 1, and tn equals previous term plus the term previous to that. So the sum of the two previous terms. Okay, and that's it for recursive.